A beam of light cuts through the darkness, again and again and again. Not randomly, not fading, perfectly timed, unstoppable. Somewhere in space, a dead star is spinning, faster than anything that should exist. Not once per minute, not once per second, but sometimes hundreds of times every single second. And with every rotation, it fires a pulse of radiation across the universe, like a cosmic lighthouse sweeping endlessly through the void. This is not a normal star. It's what remains after a star has collapsed, crushed into something so dense, so extreme, that a single teaspoon of its material would weigh billions of tons. Its magnetic field is unimaginably powerful. Its gravity bends space itself. And yet, it never stops spinning, even after millions of years. Even after everything else has faded. This is a pulsar, one of the most precise, most violent, and most mysterious objects ever discovered. And in this video from Stellar Depth, we're going to explore how something can die and still keep spinning forever. It begins with a star, not a quiet one like our sun, but a massive, short-lived giant. A star born with several times the mass of the sun, burning its fuel at an extraordinary rate. For millions of years it shines brilliantly, fusing hydrogen into helium in its core, releasing enormous amounts of energy that push outward against the crushing force of gravity. This balance between outward pressure and inward collapse is what keeps any star alive. But in massive stars, this balance is temporary. As time passes, the star begins to exhaust its hydrogen fuel. The core contracts under gravity, heating up until it becomes hot enough to fuse heavier elements. Helium turns into carbon, carbon into oxygen, and eventually, in the most massive stars, fusion continues all the way to iron. And this is where everything changes. Iron cannot release energy through fusion the way lighter elements do. Instead of producing energy, it consumes it. When a star's core becomes mostly iron, the engine that has been holding gravity back suddenly shuts down. In a fraction of a second, gravity wins. The core collapses inward violently, reaching speeds of tens of thousands of kilometers per second. Protons and electrons are crushed together, forming neutrons in a process called electron capture. The entire core transforms into an ultra-dense sphere made almost entirely of neutrons. Then, just as quickly, the collapse halts. The core has become so dense that it cannot compress any further. This sudden stop creates a powerful shock wave that blasts outward through the star's outer layers. What follows is one of the most energetic events in the universe, a supernova. For a brief moment, the dying star can outshine entire galaxies. Its outer layers are hurled into space at incredible speeds, enriching the surrounding environment with heavy elements forged during the star's lifetime and in the explosion itself. What remains behind is something completely different from the star that once existed, a neutron star. This object is incredibly small compared to the original star, typically only about 20 kilometers in diameter, yet it contains more mass than the Sun. Its density is so extreme that matter behaves in ways we can barely understand. If you could somehow stand on its surface, gravity would be billions of times stronger than on Earth. But in reality, such a surface is not something any human could experience. The conditions are far beyond anything we encounter in everyday physics. Now, this is where the story of pulsars truly begins. When the original star collapses, it doesn't just shrink, it also spins faster. This is a result of a fundamental principle in physics known as the conservation of angular momentum. Imagine an ice skater spinning with arms extended. As they pull their arms inward, their rotation speeds up dramatically. The same thing happens during the collapse of a star. A star that may have rotated slowly over days or weeks suddenly becomes an object spinning multiple times per second. In some cases, even hundreds of times per second. But rotation alone does not create a pulsar. The second key ingredient is magnetism. Massive stars already possess magnetic fields, but when the star collapses into a neutron star, those magnetic fields become intensely compressed. The result is a magnetic field trillions of times stronger than anything we can produce on Earth. This magnetic field is not aligned with the star's rotation axis. Instead, it is tilted. And that misalignment is what transforms a neutron star into a pulsar. As the neutron star spins, its powerful magnetic field accelerates charged particles near its surface to near the speed of light. These particles travel along the magnetic field lines toward the magnetic poles, where they emit beams of electromagnetic radiation. These beams shoot out into space from the poles of the neutron star. Now imagine this spinning object in motion. With each rotation, the beams sweep across space like the light from a lighthouse. If Earth happens to lie in the path of one of these beams, we detect a pulse of radiation every time the beam points toward us. That is why it is called a pulsar. From our perspective, it appears as if the object is pulsing on and off with incredible precision. But in reality, it is spinning continuously, and we are simply catching glimpses of its beams as they sweep past. Some pulsars are so precise that they rival atomic clocks. Their pulses arrive with such regularity that astronomers can predict them down to fractions of a microsecond. This stability makes pulsars incredibly valuable tools for studying the universe. But not all pulsars are the same. Some rotate slowly, completing a rotation every few seconds. Others, known as millisecond pulsars, spin hundreds of times per second. These are among the fastest spinning objects ever observed. Millisecond pulsars are believed to form in binary systems, where a neutron star pulls matter from a companion star. As it accumulates this material, it gains angular momentum and spins faster, like a wheel being driven by an external force. Over time, this process can accelerate the neutron star to astonishing speeds. Despite their differences, all pulsars share the same fundamental origin: the collapse of a massive star and the formation of a neutron star with a strong magnetic field and rapid rotation. But pulsars are not just interesting because of how they form. They are also windows into extreme physics. The conditions inside a neutron star are unlike anything else in the universe. The density is so high that atoms cannot exist in their normal form. Instead, matter is compressed into a state where neutrons are packed tightly together, possibly forming exotic phases of matter that we do not fully understand. Some theories suggest that deep inside neutron stars, particles may break down into their fundamental components, creating a sea of quarks. Others propose the existence of strange matter, a form of matter composed of strange quarks that could be more stable than normal nuclear matter. These ideas remain theoretical, but pulsars provide one of the few ways we can test them. By observing how pulsars behave, how they spin, how they slow down, how they interact with their surroundings. Astronomers can gather clues about the nature of matter under extreme conditions. Pulsars also serve as natural laboratories for studying relativity. Their strong gravitational fields can bend space-time, affecting the timing of their pulses in measurable ways. In binary systems, where two neutron stars orbit each other, these effects become even more pronounced. In fact, observations of pulsar binaries have provided some of the most important confirmations of Einstein's theory of general relativity. As the stars orbit each other, they lose energy through gravitational waves, causing their orbit to shrink over time. This effect was predicted by Einstein and later confirmed through precise measurements of pulsar timing. Such discoveries have deepened our understanding of gravity and opened new windows into the study of the universe. But beyond all the science, there is something profoundly striking about pulsars. They are the remnants of destruction. Born from the violent death of massive stars, they continue to exist as some of the most stable and predictable objects in the cosmos. They are both chaotic and precise, violent and orderly. And as they spin endlessly in the darkness, sending their beams across the universe, they remind us that even in the aftermath of destruction, something new, something extraordinary can emerge. This is only the beginning of their story. Long after the explosion has faded and the expanding shell of the supernova drifts outward into space, the neutron star at its center continues its relentless motion. It spins, not because something is pushing it, but because nothing can stop it. In the vacuum of space, there's almost no friction, no air, no resistance. Once a neutron star begins rotating, it can continue for millions, even billions of years. But over time, something subtle begins to change. The pulses slow down. Very slowly, at first, almost imperceptibly, but measurable. Every pulse carries energy away from the star. Each beam of radiation is not just light, but a loss of rotational energy. Like a spinning top that gradually loses speed, a pulsar begins to decelerate. Astronomers can track this slowdown with astonishing precision. By measuring the exact timing between pulses, they can determine how fast the pulsar is rotating and how that rotation changes over time. These measurements reveal something extraordinary. Pulsars are not perfectly stable. They evolve. The rate at which a pulsar slows down depends on several factors, including its magnetic field strength and its rotation speed. Younger pulsars tend to spin faster and lose energy more rapidly, while older pulsars slow down and become quieter over time. Eventually, some pulsars fade away completely. Their beams weaken, their pulses become harder to detect, and after millions of years, they may disappear from our observations entirely, still spinning, but no longer visible to us. But before that happens, pulsars can undergo sudden and dramatic changes. These events are known as glitches. Without warning, a pulsar that has been steadily slowing down can suddenly speed up. Its rotation rate increases slightly, and then it resumes its gradual slowdown as if nothing happened. These glitches are incredibly small, often just a tiny fraction of a percent, but they are real, measurable, and deeply mysterious. What could cause such a sudden change in something so dense, so stable, and so extreme? The answer may lie inside the neutron star itself. Although we often think of neutron stars as solid objects, their interiors are far more complex. Beneath a thin outer crust, there may exist layers of matter in exotic states, including a superfluid core. A superfluid is a state of matter that flows without resistance. Inside a neutron star, this superfluid may rotate differently from the outer crust. Over time, the rotation of the superfluid and the crust can become slightly out of sync. When the difference becomes too great, the system suddenly readjusts. The crust jerks forward, and the pulsar's rotation briefly speeds up. This is what we observe as a glitch. These events provide rare and valuable clues about the internal structure of neutron stars, a region we cannot observe directly. But pulsars do more than reveal their own secrets. They also illuminate the space around them. As a pulsar spins, it emits a powerful wind of charged particles, moving at nearly the speed of light. This pulsar wind interacts with the surrounding environment, especially if the neutron star is still embedded within the remnants of its supernova explosion. The result is a pulsar wind nebula. These nebulae are some of the most beautiful and energetic structures in the universe. They glow across multiple wavelengths, from radio waves to X-rays, powered by the energy of the spinning neutron star at their center. One of the most famous examples is the Crab Nebula, located in the constellation Taurus. At its heart lies the Crab Pulsar, a young neutron star spinning about 30 times per second. Its wind energizes the surrounding nebula, creating intricate patterns of glowing filaments and high-energy radiation. By studying these nebulae, astronomers can learn how pulsars transfer energy into their surroundings and how that energy shapes the interstellar medium. But pulsars are not always isolated. Some exist in binary systems orbiting another star. These systems can produce some of the most extreme and fascinating interactions in astrophysics. In certain cases, a pulsar may orbit a normal star and begin to pull matter from it. This material forms an accretion disk around the neutron star, gradually spiraling inward. As the pulsar gains mass and angular momentum, it spins faster. This process can transform a slow pulsar into a millisecond pulsar, one of the fastest spinning objects in the universe. These recycled pulsars can rotate hundreds of times per second with incredible stability. Some are so precise that their timing rivals the best atomic clocks ever built on Earth. This precision allows astronomers to use pulsars as tools for measuring the universe. One of the most powerful applications is the detection of gravitational waves. By monitoring a network of pulsars spread across the galaxy, known as a pulsar timing array, scientists can look for tiny distortions in space-time caused by passing gravitational waves. These waves, produced by massive events such as merging black holes, slightly alter the arrival times of pulsar signals. By analyzing these changes across many pulsars, astronomers can detect signals that would otherwise be impossible to observe. In this way, pulsars become part of a galaxy-sized detector. They allow us to sense movements in space-time itself. But even beyond these applications, pulsars continue to surprise us. Some emit not just radio waves, but also visible light, X-rays, and gamma rays. Others produce bursts of energy that appear irregular or chaotic, challenging our understanding of how they function. There are pulsars that switch their emission on and off, others that change their pulse patterns over time, and some that behave in ways we still cannot fully explain. Each new observation raises new questions. Why do some pulsars emit across multiple wavelengths while others do not? What determines the exact shape and strength of their beams? How do their magnetic fields evolve over time? And what truly lies at their core? These questions are not just about pulsars themselves. They touch on some of the deepest mysteries in physics: the behavior of matter at extreme densities, the nature of magnetic fields at unimaginable strengths, and the fundamental structure of space-time. As technology improves, astronomers are discovering more pulsars than ever before. Radio telescopes scan the sky, searching for the telltale pulses that reveal their presence. New instruments, more sensitive and more precise, are uncovering pulsars in distant regions of the galaxy and even beyond. Each discovery adds another piece to the puzzle. And yet, even with thousands of known pulsars, we have only begun to understand them, because every pulsar is slightly different. Each one carries its own history, its own environment, and its own unique behavior. Together, they form a population of objects that are both incredibly diverse and fundamentally connected. They are the remnants of massive stars, the engines of energetic nebulae, the clocks of the cosmos, and the probes of extreme physics. And as they continue to spin, endlessly, silently, and precisely, they send their signals across the vastness of space. Signals that travel for thousands of years. Signals that may one day be detected by distant civilizations. Signals that even now are reaching us, one pulse at a time. There is something almost unsettling about the precision of a pulsar. In a universe filled with chaos, exploding stars, colliding galaxies, and turbulent clouds of gas, pulsars behave with an almost mechanical regularity. Their pulses arrive on time, not approximately, not roughly, but with a consistency so exact that, over long periods, they rival the best clocks ever created by human technology. Some pulsars can keep time more accurately than atomic clocks, and that raises a deeper question. How can something born from one of the most violent events in the universe become one of the most precise objects we know? The answer lies in the nature of rotation itself. A neutron star is incredibly compact. With most of its mass concentrated into a sphere only about 20 kilometers wide, it has very little internal movement compared to larger objects. There are no oceans, no atmosphere, no shifting continents. Once it is formed, it becomes an almost perfectly rigid object. This rigidity allows it to rotate with extraordinary stability. There is very little to disrupt its motion. But even so, pulsars are not completely isolated from the rest of the universe. They exist within space, and space is not empty. As their beams travel outward, they pass through clouds of gas, magnetic fields, and interstellar plasma. These environments can slightly alter the signals we receive, stretching or delaying them in subtle ways. Astronomers must account for these effects with incredible care. By analyzing how pulsar signals change as they travel through space, scientists can actually map the distribution of matter between the stars. Pulsars become probes, allowing us to study regions of space that would otherwise be invisible. In this way, pulsars are not just objects to observe. They are tools. Tools that reveal the structure of the galaxy. Tools that measure distances across vast cosmic scales. tools that help us understand how matter is distributed in the universe. But perhaps one of the most fascinating uses of pulsars lies in their role as cosmic navigational beacons. Because their pulses are so regular, they can be used like GPS signals. In fact, scientists have explored the idea of using pulsars as a navigation system for spacecraft traveling deep into space. By measuring the arrival times of pulses from multiple known pulsars, a spacecraft could determine its position with remarkable accuracy, even far beyond the reach of Earth-based systems. In a sense, pulsars provide a natural galaxy-wide positioning system, a network of rotating stars marking the structure of space itself. But beyond navigation, pulsars also allow us to explore the fundamental laws of physics in extreme conditions. Nowhere is this more evident than in binary pulsar systems. When two neutron stars orbit each other, their interaction creates a unique laboratory for testing gravity. These systems are incredibly dense, incredibly fast, and incredibly energetic. As they orbit, they emit gravitational waves, ripples in space-time that carry energy away from the system. This causes the stars to gradually spiral closer together. Over time, their orbit shrinks, and this change can be measured. By observing the timing of pulses from one of the stars, astronomers can track the orbit with extraordinary precision. The results match exactly what Einstein's theory of general relativity predicts. This was one of the first indirect confirmations of gravitational waves, decades before they were directly detected by instruments like LIGO. Pulsars, once again, proved to be powerful tools. But even within individual pulsars, there are mysteries that challenge our understanding. One of these is the structure of their magnetic fields. The magnetic field of a neutron star is not just strong, it is unimaginably strong, trillions of times stronger than Earth's magnetic field. This field shapes everything about the pulsar. It determines how particles are accelerated. It controls the direction of the radiation beams. And it evolves over time, slowly changing the behavior of the star. But how exactly these magnetic fields form and how they behave under such extreme conditions remains an open question. Some pulsars show changes in their emission patterns. Their pulses may become weaker or stronger. They may shift in shape, or they may even disappear for periods of time before returning. These changes suggest that the magnetic field itself is dynamic, not fixed, but evolving, and that evolution may be linked to processes deep within the neutron star. Another mystery lies in the surface of these stars. Despite their extreme density, neutron stars are believed to have a thin outer crust, a solid layer composed of nuclei packed together in ways that do not exist anywhere else. This crust may crack or shift under stress, producing sudden releases of energy. In some cases, these events may be responsible for the glitches observed in pulsars. In others, they may produce bursts of radiation detectable across vast distances. And beneath this crust lies the unknown. The core of a neutron star is one of the most extreme environments in the universe. Pressures are so high that atoms cannot exist. Even nuclei may break apart. Matter may exist in forms that we cannot recreate or study directly on Earth. Understanding what happens in these conditions is one of the great challenges of modern physics. And pulsars are one of the few ways we can approach that challenge, by studying their behavior, their rotation, their emissions, and their interactions, we can begin to infer what lies within. But pulsars are not eternal. Even though they can spin for millions of years, they're gradually losing energy. Their rotation slows, their beams weaken, and eventually they may cross a threshold beyond which they no longer emit detectable pulses. When this happens, the pulsar becomes quiet. It is still there, still spinning, still dense, still extreme, but no longer visible to us as a pulsar. It becomes what astronomers sometimes call a dead neutron star. But even in this state, it remains a remarkable object, a remnant of a once massive star, a silent survivor of a violent past. And perhaps, under the right conditions, it may be reawakened. If such a neutron star exists in a binary system, it may begin to accrete matter again, gaining energy and spinning up once more. In this way, the life of a pulsar is not always a simple progression from birth to death. It can be a cycle, a transformation shaped by its environment and interactions. And throughout all of this, pulsars continue to serve as markers of the universe. Their signals travel across space, carrying information about their origin, their structure, and the space they pass through. Each pulse is a message, a precise repeating signal from a distant, spinning star. And as we continue to detect and study these signals, we deepen our understanding of the universe itself. Because in the end, pulsars are more than just spinning remnants. They are guides to the physics of extreme matter, guides to the structure of space-time, guides to the processes that shape galaxies. And as long as they continue to spin, they will continue to send their signals, steady, relentless, and precise, across the vast darkness of space. There are places in the universe where the laws of physics are pushed so far beyond anything we experience that even our best theories begin to strain. Pulsars exist in one of those places. To understand just how extreme they are, you have to imagine a world where gravity is so strong that it warps space itself, where magnetic fields are powerful enough to tear atoms apart, and where matter is compressed to densities so high that it behaves in ways we cannot fully reproduce or even observe directly. A pulsar is not just a spinning star. It is a boundary, a threshold between what we understand and what we are still trying to comprehend. At the surface of a neutron star, gravity is billions of times stronger than on Earth. If you could somehow stand there, which is impossible, you would be crushed instantly. Even light behaves differently in such an environment. Photons leaving the surface lose energy as they climb out of the gravitational well. This effect, known as gravitational redshift, stretches their wavelength, shifting them toward the red end of the spectrum. Time itself is affected. From the perspective of an outside observer, time near the surface of a neutron star passes more slowly. This is not science fiction. It is a real consequence of Einstein's theory of general relativity. In a pulsar, these relativistic effects are not just theoretical, they are measurable. Astronomers can observe how the pulses are altered by the star's intense gravity, providing direct evidence of how space-time behaves under extreme conditions. But gravity is only part of the story. The magnetic field of a pulsar is one of the most powerful forces in the known universe. To understand its scale, consider this. The strongest magnetic fields humans can produce in laboratories are measured in tens of Teslas. The magnetic field of a typical neutron star can reach trillions of Teslas. In such an environment, physics begins to change. Atoms are distorted. Electrons are forced into unusual energy states. Even the vacuum of space behaves differently, becoming polarized under the influence of the magnetic field. Light itself can be affected. In extremely strong magnetic fields, photons can split or interact in ways that are not observed under normal conditions. These quantum effects, predicted by advanced theories, may occur near the surface of neutron stars. Pulsars therefore offer a rare opportunity to observe quantum physics on a cosmic scale. But the interaction between rotation and magnetism creates something even more dramatic. As the pulsar spins, its magnetic field drags charged particles along with it. These particles are accelerated to near the speed of light, forming a magnetosphere, a region of intense electromagnetic activity surrounding the star. Within this magnetosphere, particles follow complex paths along magnetic field lines, spiraling toward the magnetic poles. As they move, they emit radiation. This radiation forms the beams that define the pulsar, but the exact mechanism behind this emission is still not fully understood. Different models attempt to explain how and where the radiation is produced. Some suggest that it originates close to the surface, near the magnetic poles. Others propose that it forms farther out, in regions where the magnetic field lines begin to open into space. The truth may involve a combination of processes. What is clear is that the emission is not simple. Pulsar beams are not uniform. They can have complex structures with multiple components and varying intensities. Some pulsars produce sharp, narrow pulses. Others emit broader, more diffuse signals. And these patterns can change over time. Some pulsars exhibit what are known as mode switches, where their emission suddenly shifts from one pattern to another. Others show drifting sub-pulses, small variations within each pulse that move in a regular way. These behaviors suggest that the magnetosphere is dynamic. It is not a static environment, but a constantly evolving system shaped by the interplay of rotation, magnetism, and particle acceleration. And yet, despite all this complexity, the overall timing of the pulses remains incredibly precise. This combination of stability and variability is one of the most intriguing aspects of pulsars. They are predictable, but not simple. Now, consider what happens at even more extreme levels. Among neutron stars, there exists a special class known as Magnetars. These objects take the concept of a pulsar and push it even further. Their magnetic fields are hundreds or even thousands of times stronger than those of typical neutron stars. In magnetars, the magnetic field dominates everything. It can twist and strain the star's crust, causing it to crack in events known as star quakes. These events release enormous amounts of energy, producing bursts of radiation that can be detected across the galaxy. Some magnetars emit powerful gamma-ray flares, among the most energetic events in the universe. In these objects, the boundary between classical physics and quantum physics becomes even more blurred. Magnetars are not just extreme. They are a glimpse into regimes of physics that we are only beginning to explore. But even ordinary pulsars, if such a term can be used, operate under conditions far beyond anything on Earth. Their study requires not only advanced technology, but also new ways of thinking, because in many cases we are observing phenomena that challenge our assumptions about how matter and energy behave. One of the key challenges in pulsar research is connecting observations to theory. We can measure pulses with incredible precision. We can observe changes over time. We can detect emissions across multiple wavelengths. But translating these observations into a complete understanding of the underlying physics is not straightforward. There are still gaps, still uncertainties, still questions that remain unanswered. What exactly determines the structure of the emission beams? How do magnetic fields evolve over millions of years? What happens in the deepest layers of the neutron star? And how do all these factors interact to produce the signals we observe? These questions drive ongoing research. New telescopes, more sensitive instruments, and advanced simulations are helping to push the boundaries of what we know. Radio arrays scan the sky for new pulsars. Space-based observatories detect high-energy emissions, and theoretical models attempt to bridge the gap between observation and understanding. Each new discovery adds another layer to the story, and sometimes it reveals something unexpected. A pulsar with an unusual rotation rate, a system with an unexpected companion, a signal that does not fit existing models. These anomalies are not problems. They are opportunities. They point to areas where our understanding is incomplete and where new insights may emerge. In this way, pulsars are not just objects of study. They are teachers. They force us to confront the limits of our knowledge. They challenge our theories, and they guide us toward a deeper understanding of the universe. Because at their core, pulsars are reminders of what happens when nature operates at its extremes, when gravity, magnetism, and rotation combine in ways that push the boundaries of physics. And as we continue to study them, we are not just learning about distant stars. We are learning about the fundamental laws that govern everything, from the smallest particles to the largest structures in the cosmos. There is a moment, just after a pulsar is born, when everything about it is at its most extreme. Its rotation is at its fastest. Its magnetic field is at its strongest. Its energy output is at its peak. This is the young pulsar phase, a period when the neutron star is still surrounded by the expanding debris of the supernova that created it, still injecting enormous amounts of energy into its surroundings, still shaping the environment around it in powerful and visible ways. In this stage, the pulsar is not alone. It exists inside a cloud of expanding gas, the supernova remnant, a vast, turbulent structure filled with shock waves, magnetic fields, and high-energy particles. The pulsar sits at the center of this expanding shell, spinning rapidly, acting as an engine that continues to energize the system long after the explosion itself has ended. The interaction between the pulsar and its environment creates something extraordinary. A pulsar wind nebula. This nebula is not simply leftover debris, it is a living structure, powered continuously by the pulsar at its center. The neutron star emits a wind of charged particles, electrons and positrons, moving outward at nearly the speed of light. This wind slams into the surrounding material, creating shock fronts where energy is converted into radiation. The result is a glowing nebula that shines across the electromagnetic spectrum. In radio wavelengths, it reveals extended structures shaped by magnetic fields. In visible light, it may show intricate filaments and faint glowing regions. In X-rays, it becomes something even more dramatic. A high-energy environment where particles are accelerated to extreme energies, producing intense radiation. The Crab Nebula is one of the most well-known examples of this process. At its center lies a young pulsar, spinning about 30 times per second, continuously injecting energy into the surrounding nebula. The entire structure glows as a result of this energy, creating one of the most studied objects in astronomy. But the Crab Nebula is not unique. There are many pulsar wind nebulae scattered throughout the galaxy, each shaped by the characteristics of its central pulsar and the environment in which it resides. Some are compact and bright. Others are diffuse and extended. Some show jets of material streaming outward along the pulsar's rotation axis, while others exhibit complex, chaotic structures shaped by interactions with the surrounding interstellar medium. These nebulae are not static. They evolve over time. As the pulsar loses energy and slows down, the wind weakens. The nebula expands and cools. Eventually, the influence of the pulsar diminishes, and the nebula fades into the background of space. But during their active phase, pulsar wind nebulae are among the most energetic and dynamic regions in the galaxy. They provide a direct window into the processes that govern particle acceleration and high-energy radiation. They also play a role in shaping the interstellar environment. The energy they inject into space can influence nearby gas clouds, potentially triggering or suppressing the formation of new stars. In this way, the life of a pulsar is not isolated. It is part of a larger system, a system that begins with a massive star, continues through a supernova explosion, and extends into the surrounding galaxy through the influence of the pulsar wind. But not all pulsars remain at the center of their birthplaces. Some are born with a kick. During the supernova explosion, asymmetries in the collapse can impart a significant velocity to the neutron star. This kick can send the pulsar racing through space at hundreds of kilometers per second. Over time, these high-speed pulsars move away from their original locations, traveling through the interstellar medium. As they move, they interact with the gas around them. If a pulsar is moving fast enough, it can create a bow shock, a structure similar to the wave that forms at the front of a boat moving through water. This bow shock compresses and heats the surrounding gas, producing a distinctive arc-shaped structure. Behind the pulsar, a trail of energized particles may form, creating a comet-like tail that extends across space. These moving pulsars add another layer of complexity to the study of neutron stars. They show that pulsars are not just static beacons, but dynamic objects that can travel across the galaxy, carrying their energy and influence with them. And as they move, they continue to emit their pulses, signals that sweep across space, independent of their motion. Signals that can be detected even as the pulsar travels thousands of light years from its birthplace. But perhaps one of the most fascinating aspects of pulsars is how they interact with companions. In binary systems, the presence of another star can dramatically alter the evolution of a pulsar. If the companion star is close enough, the pulsar's gravity can begin to pull material from it. This material forms an accretion disk, spiraling inward toward the neutron star. As it falls, it heats up, emitting X-rays and other high-energy radiation. At the same time, the transfer of mass and angular momentum can spin up the neutron star, This is how millisecond pulsars are created. Originally slow and aging, the neutron star is recycled by its companion, gaining speed and becoming one of the fastest rotating objects in the universe. These systems are not always stable. In some cases, the pulsar's radiation can begin to strip material from its companion star, gradually eroding it over time. These are known as black widow pulsars. In these systems, the pulsar is literally destroying its companion. The intense radiation and particle wind from the neutron star heat and evaporate the companion star, causing it to lose mass. Over time, the companion may be reduced to a fraction of its original size, or even completely destroyed. This process is slow, but relentless, and it highlights the extreme nature of pulsars. Even long after their formation, they remain powerful enough to influence and even destroy nearby objects. But not all interactions are destructive. Some binary pulsars exist in stable orbits, where both stars influence each other in measurable ways. In systems where both objects are neutron stars, the interaction becomes even more fascinating. These double neutron star systems are rare, but incredibly important. They provide opportunities to study gravity, orbital dynamics, and the emission of gravitational waves in ways that are not possible elsewhere. As these stars orbit each other, they gradually lose energy, spiraling closer together. Eventually, they may merge, and when they do, the result is one of the most powerful events in the universe, a kilonova, accompanied by a burst of gravitational waves and electromagnetic radiation. These events are responsible for creating some of the heaviest elements in the universe, including gold and platinum. In this way, pulsars are connected to processes that shape not just stars but the very composition of matter. They are part of a chain of events that begins with the birth of massive stars and ends with the creation of elements that become part of planets and life itself. And yet, through all of this, through their interactions, their movements, their evolution, pulsars continue to do one simple thing. They spin relentlessly, sending out their pulses marking time in the darkness of space. Each pulse a reminder of their origin. Each rotation a continuation of a process that began in the collapse of a star. And as long as they continue to spin, they will continue to shape the universe around them. Not just as remnants of the past, but as active participants in the ongoing story of the cosmos. There is a point in the life of a pulsar where its story becomes quieter, but no less important. After millions of years of spinning, radiating, and gradually losing energy, the pulsar begins to slow down. Its once rapid rotation becomes more measured. Its beams, once powerful and easily detectable across vast distances, begin to weaken. This stage is not dramatic. There is no explosion, no sudden collapse, no visible transformation. Instead, the pulsar simply fades. But this fading process reveals something essential about how these objects evolve, and how they eventually transition into a different kind of existence. At the heart of this transformation is energy. A pulsar is powered by its rotation. Every pulse it emits carries away a tiny amount of that rotational energy. Over time, this loss accumulates, and the pulsar's spin gradually decreases. This process is known as spin down. Astronomers can measure it with extraordinary precision. By tracking the timing of pulses over years or even decades, they can determine how quickly a pulsar is slowing and how much energy it is losing. This allows scientists to estimate the age of a pulsar. Young pulsars spin rapidly and lose energy quickly. Older pulsars spin more slowly and lose energy at a much lower rate. Eventually, the pulsar reaches a point where it can no longer sustain the processes that produce its beams. This boundary is sometimes referred to as the death line. It is not a physical barrier, but a theoretical threshold. Beyond this point, the pulsar's magnetic field and rotation are no longer strong enough to accelerate particles and generate detectable radiation. The pulses stop. From our perspective, the pulsar disappears, but the neutron star itself remains. It continues to exist as an incredibly dense, compact object, still spinning, still carrying its immense magnetic field, but no longer visible as a pulsar. This is what astronomers call a dead neutron star. Yet even in this quiet state, the story is not always over. In some cases, the environment can bring the neutron star back to life. If a dead neutron star exists in a binary system, it may begin to interact with a companion star. As matter flows from the companion onto the neutron star, it can transfer angular momentum, causing the neutron star to spin faster. This process can reignite the pulsar mechanism. The star begins emitting pulses again. It is reborn, not as a young pulsar, but as a recycled one. These recycled pulsars are among the most fascinating objects in the universe. They spin incredibly fast, often hundreds of times per second, and exhibit remarkable stability. Their pulses are so regular that they can be used as precise timekeeping tools, rivaling even the best atomic clocks. This stability makes them ideal for a variety of scientific applications. One of the most important is the study of gravitational waves. By monitoring an array of millisecond pulsars distributed across the sky, astronomers can detect subtle variations in the timing of their pulses. These variations may be caused by gravitational waves passing through space, stretching and compressing the fabric of space-time. This technique, known as pulsar timing arrays, allows scientists to probe gravitational waves at frequencies that are difficult to detect with other methods. In this way, pulsars become part of a vast cosmic observatory. They help us study events occurring billions of light-years away. They allow us to detect the motion of massive black holes, the merging of galaxies, and other large-scale phenomena that shape the universe. But beyond their role as tools, pulsars also provide insight into the long-term evolution of stars. They represent one possible endpoint in the life cycle of massive stars. A star is born from a cloud of gas. It lives, burns, and evolves. It dies in a supernova, and it leaves behind a neutron star. That neutron star may become a pulsar, spinning and emitting radiation for millions of years, and eventually it may fade into silence. This cycle is not unique. It is part of a larger pattern that repeats throughout the galaxy. Every generation of stars contributes to the next. The material ejected in supernova explosions enriches the interstellar medium, providing the building blocks for new stars and planets. Pulsars, as remnants of these explosions, are part of this ongoing process. They are markers of past events and contributors to future ones. But perhaps one of the most intriguing aspects of pulsars is how they challenge our understanding of matter itself. Inside a neutron star, matter exists under conditions that cannot be replicated in laboratories. The densities are so high that atoms are crushed together. Electrons and protons combine to form neutrons. and even those neutrons may break down under extreme pressure. Some theories suggest that the cores of neutron stars may contain exotic forms of matter, quark matter, strange matter, phases of matter that exist only under the most extreme conditions. These ideas are still speculative, but pulsars provide one of the few ways to test them. By studying how neutron stars behave, how they spin, how they cool, how they respond to disturbances, scientists can infer properties of the matter inside them. For example, the way a pulsar glitches, suddenly changing its rotation rate, may provide clues about the interaction between different layers within the star. The way it emits radiation may reveal information about its magnetic field structure. The way it slows down may indicate how energy is distributed within it. Each observation adds another piece to the puzzle, and yet, despite decades of study, many questions remain unanswered. What is the true nature of matter at nuclear densities? How do magnetic fields evolve over time? What determines the exact behavior of a pulsar's emission? These questions are not just about pulsars. They are about the fundamental laws of physics. They connect to theories of quantum mechanics, nuclear physics, and general relativity. They push the boundaries of what we know and what we can know. And that is what makes pulsars so important. They are not just objects in space. They are experiments. Natural experiments conducted on a scale and under conditions that we cannot reproduce on Earth. By observing them, we are observing physics in its most extreme form. We are testing our theories against the universe itself. And sometimes, the universe surprises us. It behaves in ways we did not expect. It reveals phenomena we had not predicted. It challenges our assumptions. And it forces us to rethink our understanding. Pulsars are part of that process. They are both familiar and mysterious. We can detect them. We can measure them. We can predict their behavior. And yet, there is still so much we do not understand. As they continue to spin, slowly losing energy, gradually evolving, they carry with them the history of their origin and the potential for new discoveries. Even as they fade, they remain important. Even as they grow quiet, they continue to exist as relics of some of the most powerful events in the universe. And perhaps, under the right conditions, they may begin again, spinning faster, emitting pulses, returning to life. Because in the universe, even something that seems to have ended may only be waiting for the right moment to start again. There are moments in astronomy when an object does more than exist. It becomes a signal, not just a point of light, not just a distant source of radiation, but something structured, something repeating, something that carries information. Pulsars are exactly that. Each pulse they emit is not random. It is not chaotic. It is a pattern, a precise, repeating signal that travels across the galaxy. And when those signals were first discovered, they did not immediately make sense. In fact, they raised a question that, for a brief moment, changed the way scientists looked at the sky. When the first pulsar was detected in 1967, it appeared as a regular series of radio pulses arriving with perfect timing. The signal was so consistent, so precise, that it did not resemble any known natural phenomenon. It pulsed like a clock, seconds, fractions of seconds, perfectly spaced. At first, there was no explanation. No known star behaved like this. No known object could produce such a clean, repeating signal. And so, naturally, one possibility was considered. Could it be artificial? Could it be a signal from an intelligent source? The idea was not dismissed immediately. In fact, the first pulsar was jokingly labeled LGM-1, short for Little Green Men. But as more pulsars were discovered, each with its own distinct timing and characteristics, it became clear that this was not a single, isolated signal. It was a class of objects, a new kind of star. And with that realization, pulsars became something even more fascinating. They were not messages from another civilization. They were messages from physics itself. Signals that revealed how matter behaves under extreme conditions. Signals that could be used to measure time, distance, and motion across the universe. Signals that turned neutron stars into some of the most useful tools in astronomy. But the idea of pulsars as signals did not disappear. In fact, it evolved. Because if pulsars produce such precise, detectable patterns, then they can be used not only to study the universe, but also to navigate it. Imagine a spacecraft traveling far beyond the reach of Earth. No GPS, no direct communication, no reference point, only the stars. If that spacecraft can detect pulsar signals, it can determine its position by comparing the timing of pulses from different directions. Each pulsar acts like a beacon, a fixed point in space with a known pattern. By measuring the arrival times of these pulses, the spacecraft can triangulate its location, much like how GPS satellites work on Earth. This concept is not theoretical. It has already been tested. Experiments have demonstrated that pulsar-based navigation is possible, offering a way for future missions to travel independently through deep space. In this way, pulsars become part of a cosmic infrastructure, a natural system of markers embedded in the galaxy. And yet, beyond navigation, there's another idea that continues to capture the imagination. If the pulsars are detectable across vast distances, could they be used for communication? Not by us, but by someone else. The precision of pulsar signals makes them ideal for encoding information. A civilization with advanced technology could, in theory, modulate a pulsar signal, altering its timing or intensity to transmit a message. This idea has been explored in scientific discussions and even in the search for extraterrestrial intelligence. So far, no evidence has been found to suggest that any pulsar signals are artificial. They appear to be entirely natural. But the possibility remains an intriguing one, because pulsars demonstrate that the universe itself is capable of producing signals that resemble communication, patterns, repetition, structure, all emerging from physical processes. And that raises a deeper question. What is the difference between a natural signal and an artificial one? At what point does a pattern become a message? These questions extend beyond pulsars. They touch on the nature of information, the limits of detection, and the way we interpret signals from the universe. But even without invoking the possibility of communication, pulsars are already remarkable in what they reveal. Their signals allow us to measure distances across the galaxy. By analyzing how pulses are dispersed as they travel through interstellar plasma, astronomers can estimate how much material lies between us and the pulsar. This provides information about the structure of the Milky Way. It allows scientists to map regions that are otherwise invisible. Pulsars also help us measure motion. If a pulsar is moving relative to Earth, its pulses may shift slightly in frequency due to the Doppler effect. By studying these shifts, astronomers can determine how fast the pulsar is moving and in what direction. In binary systems, pulsar signals can reveal the motion of both stars. The timing of pulses changes as the pulsar moves toward and away from us, allowing scientists to reconstruct the orbit with incredible accuracy. This has led to some of the most precise measurements in astrophysics: masses of neutron stars, orbital dynamics, tests of gravity, all derived from the careful study of pulsar signals. But perhaps the most profound use of pulsars as signals lies in their ability to detect disturbances in space-time itself. When a gravitational wave passes between a pulsar and Earth, it slightly alters the distance between them. This change affects the arrival time of the pulses. By monitoring many pulsars simultaneously, astronomers can look for correlated changes in timing, patterns that indicate the presence of gravitational waves. This method allows scientists to detect waves from sources that are too large or too slow to be observed by other detectors. In this sense, pulsars are not just signals. They are sensors, sensitive to changes in the fabric of the universe, sensitive to events occurring far beyond our immediate surroundings. And as we continue to observe them, we are not just listening to distant stars, we are listening to the universe itself. But there is still something deeply human about the way we perceive pulsars. We hear them as pulses, as rhythms, as patterns, and we interpret those patterns through the lens of our own understanding. We assign meaning, we look for structure, we search for connections, and in doing so, we transform these distant signals into something familiar, something understandable. Yet at their core, pulsars remain what they have always been: spinning neutron stars, born from collapse, driven by rotation, emitting beams of radiation into the vastness of space. They do not intend to communicate. They do not carry messages. And yet, in their precision, in their repetition, in their unwavering rhythm, they become something more. They become markers of time, beacons of physics, and reminders that even in the silence of space, there are patterns waiting to be discovered. Patterns that, once understood, can reveal the deepest truths about the universe, one pulse at a time. There is a limit to how fast anything in the universe can spin. Not because something forces it to stop, but because the laws of physics themselves impose boundaries. For pulsars, that limit is pushed to the extreme. Some neutron stars rotate so quickly that they approach a point where any further increase in speed would tear them apart. These are the millisecond pulsars, objects that spin hundreds of times every second, completing a full rotation in just a few milliseconds. To understand how extreme this is, imagine something the size of a city, about 20 kilometers across, spinning faster than a kitchen blender. At such speeds, the surface of the neutron star moves at a significant fraction of the speed of light. And yet, it holds together. The reason lies in its gravity. A neutron star is so dense, so compact, that its own gravity is strong enough to counteract the enormous centrifugal forces trying to rip it apart. This balance allows it to maintain its structure even at incredible rotation rates. But there is a theoretical limit. If a neutron star spins too fast, the outward forces at its equator would exceed the inward pull of gravity. At that point, matter would begin to be flung off into space. This maximum rotation rate is known as the breakup limit. Astronomers have observed pulsars spinning close to this limit, but not beyond it. The fastest known pulsars rotate over 700 times per second, a rate that approaches the boundary of what is physically possible. Why don't we see pulsars spinning even faster? The answer may lie in the processes that spin them up. As discussed earlier, millisecond pulsars are thought to form in binary systems, where a neutron star gains mass and angular momentum from a companion star. This process gradually increases the pulsar's rotation rate, but as the pulsar spins faster, other effects begin to counteract this acceleration. One possibility involves gravitational waves. If a neutron star is not perfectly symmetrical, if it is even a tiny distortion in its shape, its rapid rotation can produce gravitational waves. These waves carry energy away from the star, limiting how fast it can spin. In this way, the emission of gravitational waves acts as a brake. It prevents the pulsar from reaching even higher rotation rates. Another possibility involves the structure of the neutron star itself. At extreme rotation speeds, the internal stresses within the star may reach a point where the material can no longer maintain its shape. This could lead to changes in the star's structure, affecting its rotation. These limits are not just theoretical, they are supported by observations. Despite decades of searching, astronomers have not found pulsars spinning beyond certain speeds. This suggests that there is indeed a natural boundary, one defined by the interplay of gravity, rotation, and energy loss. But rotation is only one aspect of a pulsar's extreme nature. Another is its shape. At slower speeds, a neutron star is nearly spherical. But as it spins faster, it begins to flatten at the poles and bulge at the equator. This is similar to what happens to planets like Earth and Jupiter, but on a much more extreme scale. In rapidly rotating pulsars, this deformation can be significant. The star becomes an oblate spheroid, slightly squashed along its axis of rotation. This shape affects how the pulsar emits radiation. It can influence the structure of the magnetic field, the distribution of particles in the magnetosphere, and the characteristics of the emitted pulses. In some cases, these effects may be detectable. Changes in pulse shape, timing variations, and other observational signatures can provide clues about the geometry of the neutron star. But even more intriguing is the possibility that neutron stars are not perfectly smooth. Their surfaces may contain irregularities, tiny mountains, or deformations that, while small in absolute terms, are significant given the star's size and density. These irregularities could play a role in the emission of gravitational waves. A perfectly symmetrical rotating object does not produce gravitational waves, but a slightly asymmetrical one does. Even a deformation just a few centimeters high could be enough to generate detectable waves if the star is spinning fast enough. This opens the possibility of using pulsars as sources of continuous gravitational waves. Unlike the bursts produced by merging black holes or neutron stars, these signals would be steady and persistent, offering a different way to study the universe. Detecting such waves is extremely challenging. The signals are weak and the noise is significant. But advances in technology and data analysis are bringing us closer to this goal. If successful, it would provide a new window into the structure of neutron stars, a way to probe their internal properties without ever seeing inside them. But even without direct detection, the study of pulsar rotation continues to reveal important insights. For example, the relationship between rotation rate and magnetic field strength provides clues about how neutron stars evolve. Young pulsars tend to have strong magnetic fields and slower rotation rates. As they age, their magnetic fields may decay and their rotation slows. But in binary systems, this trend can be reversed. Accretion can spin up the neutron star, creating a fast-spinning, low magnetic field pulsar. These patterns help astronomers classify pulsars and understand their life cycles. They reveal how different factors, initial conditions, environment interactions, shape the evolution of these objects. But beyond classification, there is a deeper significance. Pulsars operate at the limits of what is physically possible. They test the boundaries of our theories. They challenge our understanding of matter, energy, and space-time. And they do so in a way that is both observable and measurable. Each rotation, each pulse, each subtle change in timing or intensity, all of it carries information. Information about the structure of the star, information about the forces acting within it, information about the universe around it. And as we continue to study these signals, we refine our understanding. We develop new models, we test new ideas, we push closer to the limits of what we can know. But there is always a boundary, a point beyond which our current theories may no longer apply. And pulsars exist right at that boundary. They are not just extreme objects. They are edge cases, examples of what happens when the fundamental forces of nature are pushed to their limits. And in studying them, we are not just learning about neutron stars. We are exploring the very edges of physics itself, a place where gravity, quantum mechanics, and electromagnetism converge, a place where the familiar begins to break down, and where new understanding begins to emerge. One rotation at a time. There is a moment in the life of every pulsar when its presence becomes almost impossible to detect. Not because it has stopped existing, not because it has collapsed or been destroyed, but because the mechanism that once made it visible to the universe has simply faded. The beams weaken, the pulses grow faint, and eventually they fall below the threshold of what our instruments can detect. From our perspective, the pulsar disappears. But in reality, the neutron star remains, silent, dense, and still spinning. This stage marks a transition, a shift from an active pulsar to what is often called a dormant or inactive neutron star. And while it may no longer be observable as a pulsar, its story is far from over. Because even in silence, neutron stars continue to interact with their environment in subtle and sometimes unexpected ways. One of the key factors in this late stage is the gradual decay of the magnetic field. Over millions of years, the intense magnetic field that once powered the pulsar begins to weaken. The exact mechanisms behind this decay are still not fully understood, but it likely involves processes within the star's crust and core, where currents that sustain the magnetic field slowly dissipate. As the magnetic field weakens, its ability to accelerate charged particles diminishes. Without these accelerated particles, the pulsar can no longer produce the beams of radiation that define it. The lighthouse effect fades, and the neutron star becomes quiet. But quiet does not mean inactive. In some cases, these old neutron stars can still be detected through other means. For example, they may emit thermal radiation, heat left over from their formation slowly cooling over time. This radiation is faint and often detectable only in X-ray wavelengths, requiring sensitive instruments to observe. By studying this cooling process, astronomers can learn about the internal composition of neutron stars. The rate at which a neutron star cools depends on the properties of the matter inside it, including whether exotic forms of matter are present. Thus, even a silent neutron star can provide valuable information. But perhaps more intriguing is what happens when a neutron star encounters new material. In regions of space where gas is present, a neutron star may begin to accrete matter, pulling in surrounding material through its gravitational influence. This process can lead to the formation of an accretion disk, where gas spirals inward, heating up and emitting radiation. In some cases, this can reactivate the neutron star in a different way. Instead of emitting regular pulses, it may become an X-ray source, producing bursts of high-energy radiation as material falls onto its surface. These systems are known as X-ray binaries. They represent another phase in the life of a neutron star, one driven not by its own rotation, but by its interaction with a companion or its environment. In such systems, the neutron star can undergo cycles of activity. Periods of accretion may be followed by quiescent phases, where the system becomes quieter again. Over time, the accumulation of matter can also affect the neutron star's rotation. As angular momentum is transferred, the star may spin up once more, potentially re-entering the pulsar phase. This possibility that a neutron star can move between different states highlights the complexity of its evolution. It is not a simple, linear process. It is dynamic, responsive to external conditions, capable of transformation. But beyond individual stars, there is a larger question. What happens to neutron stars over cosmic timescales? Over billions of years, as galaxies evolve and environments change, neutron stars continue to exist as long-lived remnants. They are among the most durable objects in the universe. Unlike massive stars, which burn out quickly, or even planets, which can be disrupted by stellar evolution, neutron stars can persist for immense periods of time. They become part of the background population of the galaxy, invisible, silent, but still present. Some may drift through interstellar space, remnants of past supernova, carrying with them the memory of their origin. Others may remain bound in systems, continuing to interact with companions or surrounding material. And some may eventually encounter other compact objects. When two neutron stars come close enough, their mutual gravity can lead to a merger. These events are rare, but when they occur, they are among the most powerful in the universe. The collision of two neutron stars produces a burst of gravitational waves, followed by a kilonova, an explosion that emits both light and heavy elements. These events are now observed directly, providing insights into the behavior of matter at extreme densities and the origin of elements like gold and platinum. In this context, neutron stars, and by extension pulsars, are part of a much larger cosmic cycle. They begin as the remnants of massive stars. They evolve through different phases, sometimes active, sometimes quiet, and in some cases, they end in dramatic mergers that reshape their surroundings. But even beyond these events, there is a deeper significance. Neutron stars represent one of the possible endpoints of stellar evolution. They are what remains when gravity overwhelms nuclear processes, but not enough to form a black hole. They occupy a unique position between the familiar world of stars and the extreme realm of black holes. Studying them helps us understand that boundary. It helps us explore the conditions under which matter collapses and the factors that determine the final outcome of a star's life. And pulsars, as the observable phase of neutron stars, provide a window into this process. They allow us to track the evolution of these objects from their energetic beginnings to their quieter, later stages. They show us how rotation, magnetism, and environment interact over time. They reveal patterns that can be studied, measured, and understood. But they also remind us of something more subtle: that not everything in the universe remains visible, that some objects, once bright and active, can fade into silence, and that this silence does not mean absence, it means transformation. Because even when a pulsar stops pulsing, it continues to exist. It continues to carry its mass, its gravity, its history. It continues to move through space, part of the vast structure of the galaxy. And in that quiet existence, it remains a part of the universe's ongoing story. A story that does not end with visibility. A story that continues even when the signals fade. And perhaps, under the right conditions, a story that can begin again. At some point, the pulses become so faint that they blend into the background of the universe. Not gone, just indistinguishable. What was once a precise rhythmic signal, a beacon cutting through space with perfect timing, fades into silence. The neutron star continues to spin, but no longer announces its presence, no longer sends its steady flashes across the galaxy. From our perspective, the story seems to end there. But the universe rarely works in endings. It works in transitions. Because even when a pulsar can no longer be seen as a pulsar, it still exists as one of the most extreme objects ever created. A sphere of matter so dense that it defies intuition, a remnant of a star that once burned brightly, collapsed violently, and then spent millions of years marking time with its rotation. That history does not disappear. It remains encoded in the object itself, in its mass, in its spin, in its internal structure, in the way it interacts, even subtly, with the space around it. And if we step back, if we look beyond the individual object, the story becomes larger. Pulsars are not isolated phenomena. They are part of a cosmic chain, a sequence that begins in cold, dark clouds of gas, regions where gravity slowly pulls matter together, forming stars. Those stars live their lives, shining for millions or billions of years, depending on their mass. The most massive among them burn fast and die young, and when they die, they do not fade quietly. They explode, a supernova, an event so powerful that it briefly outshines entire galaxies, tears the star apart, scattering heavy elements into space. At the center of that explosion, something remains, a neutron star. And in many cases, that neutron star becomes a pulsar. So every pulsar is a continuation of something that came before, a transformation, not a beginning. And in time, it will also become part of something that comes after. Because the material expelled in the supernova does not vanish. It spreads through space, it mixes with other gas and dust, and eventually it becomes part of new stars, new planets, new systems. This is how the universe evolves, not through isolated events, but through cycles, birth, evolution, collapse, redistribution, and then birth again. In this sense, pulsars are both remnants and contributors. They are the result of past processes, and they influence future ones. They inject energy into their surroundings. They shape the interstellar medium. They participate in interactions that can lead to new structures, new stars, and new phenomena. But beyond their role in cosmic cycles, pulsars have also changed the way we observe the universe. Before their discovery, the idea of using a star as a precise clock would have seemed unlikely. Stars were seen as dynamic, variable, often unpredictable. Pulsars challenged that view. They showed that under certain conditions, nature can produce objects of extraordinary precision. Objects that can be used not just to observe the universe, but to measure it. Through pulsars, we have tested theories of gravity. We have detected gravitational waves. We have mapped the distribution of matter in the galaxy. We have explored the behavior of matter at densities far beyond what we can achieve on Earth. All of this from objects that are in essence the remnants of stellar death. There is something deeply paradoxical in that from destruction comes precision, from collapse comes structure, from the end of a star comes one of the most reliable signals in the universe, and yet, this is a pattern that appears again and again in astrophysics. Extreme conditions lead to extreme outcomes, and those outcomes often reveal new layers of understanding. But even with all that we have learned, pulsars remain, in many ways, incomplete. There are still questions, still uncertainties, still aspects of their behavior that we do not fully understand. The exact mechanisms of their emission, the nature of their internal structure, the evolution of their magnetic fields, the limits of their rotation. These are not small details. They are fundamental questions. And answering them will require new observations, new theories, and new ways of thinking. Future telescopes will detect more pulsars, more distant ones, more unusual ones, systems we have not yet imagined. Each new discovery will add to the picture, and perhaps eventually we will reach a point where the behavior of pulsars is no longer mysterious, where we can fully describe their structure, their evolution, their role in the universe. But even then, their significance will remain, because pulsars are not just objects to be understood. They are examples. Examples of what happens when the universe pushes its own limits, when gravity compresses matter to its extreme, when magnetic fields reach unimaginable strengths, when rotation approaches the boundaries of physical possibility. They are reminders that the universe is capable of producing conditions far beyond anything we experience in everyday life, and that by studying those conditions, we can expand our understanding of what is possible. But perhaps the most striking aspect of pulsars is not their physics, it is their persistence. They spin, relentlessly, silently, for millions of years. Long after the explosion that created them has faded, long after the surrounding nebula has dispersed, long after the star that once existed is gone, they remain, turning, emitting, marking time. And even when their signals fade, even when they become invisible to our instruments, they continue to exist, hidden, quiet, but still part of the universe, still carrying the imprint of their origin, still influencing the space around them, however subtly. And perhaps that is what makes them so compelling. Not just their extremes, not just their precision, but their continuity. They are not moments, they are durations, processes that unfold over immense spans of time. And as we observe them, as we measure their pulses, as we study their behavior, we are not just looking at distant stars, we are looking at time itself, encoded in rotation, measured in pulses, stretching across millions of years, one turn after another, unbroken, unstoppable, until eventually even that motion begins to slow, not suddenly, not dramatically, but gradually, quietly, as all things in the universe do. And when that happens, the pulsar does not vanish. It simply becomes something else, another stage, another form, another step in the endless evolution of the cosmos, a reminder that in the universe nothing truly ends. It only changes, and somewhere, even now, in the darkness between the stars, there are pulsars still spinning, still sending their signals, still marking time, waiting to be discovered, waiting to be understood, one pulse at a time.